action is right. Okay, so yesterday we talked about what conics are and where they come from. Today we're going to start practically applying them. Today's January 23rd, 2013, and if I do my job correctly, you will go from hating René Descartes for inventing the system of graphing to possibly even appreciating him for inventing the system of graphing. Because if you had to learn these conics without them, you'd be truly hating life. We're going to start with ellipses, and specifically circles. Now, the locus of a circle is fairly simple. Locus, as I said yesterday, is the rule that governs a conic. And the locus of a circle is all points equidistant from a central point. Now, the simplest way in the world to graph a circle is back in polar form. In polar form, as you guys learned, and some of you forgot on the last test, which we'll get back tomorrow, or maybe later today, come looking for me. If I just wrote the radius equals 3, that's my way of fulfilling this locus. This says all the points are 3 units away from this central point we're talking about. In this case, that would be the origin. To get from polar form to Cartesian form for this, we would square both sides, and you would remember that the radius in polar form is x squared plus y squared. And so x squared plus y squared equals 9 is the equation which graphs a circle centered at the origin with a radius of 3. A little review of polar coordinates there. Any questions on this idea? I'm going to show it to you again in another way, but is that pretty straightforward? And did you guys remember that equation from the polar unit all of last week? So long ago. You guys get this is the rule of a circle, right? All the points equal from a center. Okay. But I don't believe from what I've read that René Descartes started out with polar form. He started out with the goal of bringing the works of Euclid and Pythagoras and all the rest onto his coordinate system. So instead of just saying a circle was all the points equally distant from some point, he had the idea that if you start with a specific x and a specific y the same distance, you'll get this xy point. You can also create a right triangle. We've done this a lot with the unit circle with polar coordinates. I'm sorry, that won't be that y. Put that in the wrong place. This distance will be some specific x, and this height will be some specific y. First rule of triangles that you guys learned about. Probably second rule. First rule you probably learned is that all the angles add up to 180 degrees. Second thing you probably learned about right triangles anyway was the Pythagorean theorem. So x squared, x will be this length, plus y squared, y will be this height, equals the hypotenuse squared, which is going to be the radius of this circle. So you've got 2 ways to remember the equation that describes every single point on a circle going all the way around the origin. It's x squared plus y squared equals the radius squared. If you really liked what we did with polar coordinates last week, you can maybe remember it this way. If you prefer to think of the Pythagorean theorem, you can think of every point on a circle as creating a right triangle, like on the unit circle. And then the Pythagorean theorem tells us that x squared plus y squared equals the radius of the circle squared. And that is a circle, which is the simplest form of an ellipse. Any questions on that idea? You guys good with that?
Don't erase it
May I erase this part?
yet. Not the drawing, polar form.
Okay, I'll leave the drawing up. Okay. I'll be setting up a 2-camera shoot at some point, just so I can move from board to board and edit it later. Okay. What if the circle? Yeah. Okay. What if the circle is not centered at the origin then? What if the circle is centered somewhere at some point, and I'm going to call this point, I'm going to call it K, H. Yep. So here's a circle sitting on the Cartesian plane. It's centered at a point I'm going to call K, H. K is the x-coordinate, H is the y-coordinate. And it's got a radius because all circles do. There's a fairly simple pattern to this. I'm not going to go into too much depth today. I might later with parabolas on why this pattern works the way it does. But the fairly simple pattern is, if it's centered at K, H, and has a radius of r, instead of x squared plus y squared equals r squared, you get x minus the x-coordinate squared plus y minus the y-coordinate squared equals r squared. Both of these shifts, in this case, we talked about this before with sines and cosines, but both of these are what I always call counterintuitive shifts, which means they go the opposite of the direction you would be most likely to first guess. For example, if you see minus in with an x, x means left and right, and a minus sign, which direction is negative on the x-axis, left or right? Everyone is pointing to their left. Excellent. Exact opposite. If you see x minus 5, that means you move 5 units to the right. In this case, h is also counterintuitive. I used h as a letter before with sinusoidal, I think, functions, sines and cosines, and it was intuitive. It's not when it's inside an operation with the y. These are both counterintuitive. So if you see y plus something, you actually go down. If you see y minus something, you actually go up. So for example, if I wanted to graph x minus 5 squared plus y plus 3 squared equals 16. Where do you think the center of that circle is? What are the coordinates of the center of that circle? You're giving me the radius.
Well, no, I was giving you the quadrant.
Oh, you're giving me the quadrant. Okay, that's good. Gotcha. That is in quadrant 4. What are the actual points?
5.
5, negative 3. And now, what's the radius of this circle?
4.
Same number of fingers. Thank you, Robbie. 4. That'll be centered at 5, negative 3 with a radius of 4. I'm going to go back over here to graph it. Now let's see. When you're graphing these things, you have to pick your, we know it's in quadrant 4 actually, so I'm going to draw my graph differently. You have to pick your axes and your origin and your scaling carefully. There's going to be a lot of graphing in this unit. I suggest you get some graph paper where the axes are not preset and you can draw them yourselves. And I suggest you get a ruler, because you're going to want to make your own axes and your own scales on some of these. Okay, I know I'm going to need to go 1, 2, 3, 4, 5 to the right. for my x minus 5. That's my counterintuitive shift. We normally think of minus to the left, but when it's x minus a number inside an operation, we go to the right. I know I'm going to need to go 3 down because I had y plus 3. So we change the sign. It's a counterintuitive shift up and down when the shift is inside an operation with the y. That's going to be my center. Now if I get my own graph paper, make my own graph, I can't just include that. My radius was 4. So I will have to have left room to go 1, 2, 3, 4 more units to the side, past the center, and in this case, 4 units farther down from the center. Regardless of what the directions in your book say, if you're graphing a circle or an ellipse, I want to see what I call the 4 points of the compass. So I want you to label the center 5, -3. Radius of the circle is 4. Tell me what point is 4 units directly above 5, -3.
Just 4 units above.
Directly above 5,
Five,
-3.
one.
Oh, what, -3?
5, 1.
So 5.
Robbie got the question. I didn't
Oh,
ask
wait,
well.
goes 5. Okay, wait.
4
never mind.
units directly above 5, -3 is 5, -2, -1, 0, 1, 5, 1. So that's my uppermost point of my circle. I shouldn't really put a dot there. That would be confusing on the 5. Okay, someone other than Robbie. Perhaps someone wants to redeem themselves. Give me the coordinates of the point 4 units to the right of 5, -3.
9.
9 what?
-3.
9, -3. So you added 4, you added the radius to your x coordinate, did not change your y. Someone other than Robbie or Danny, what is 4 units below 5, -3?
5, -7.
Very good. Let's say 3, 4, 5, 6, 7. I did stop at the right place. Remy, I think that leaves you. I need a point that's 4 units to the left of 5, -3.
1,
Excellent. Subtract 4 from the x, change nothing about the y. I know what my circle is going to look like, so I'm trying to label these carefully. And that's how I would expect you to graph your circle. I want you to label the center, even though the center is not part of the circle. You guys think you can handle this idea?
No.
No? All right. Good luck with that, then. Can I start erasing up here?
Yeah. How'd you get all right?
Pardon?
How'd you get all right?
This square root, it's always, just erased it. X squared plus y squared equals r squared. What I just erased equals 16. Square root of 16 is 4. All right. Can I erase the circle?
Are we going to want
Yeah, you go.
If your points are labeled correctly, I'm not going to grade you on how neat your circle is, so I don't know if you'll need a compass. But if you want one, that'd be great. Yeah. Now I'm going to go back a step now. A circle centered at the origin, in general, can be x squared plus y squared equals r squared, where r is the radius. What would happen if I divided every term in this equation by r squared? What would that look like?
X squared over plus y squared over r.
Could do it that way, but I'm going to do it one term at a time.
Plus y squared over r squared.
What would that equal?
0. If you,
What?
oh, 1.
Thank you, Danny. Good catch. Incidentally, that boom mic is so good. I noticed on YouTube, I'm not sure that anyone listening can hear your guys' contributions at all. I'm not sure what to do about that.
Wait, it's not so good or it is so good?
It's not great at hearing like what you guys say. It's picking up what I say perfectly. So I have to repeat your questions, I think, for Trey or anyone else listening. So x squared over r squared plus y squared over r squared equals 1. This could be a valid way to write the equation of a circle. If you saw this, I'd like you to remember this and think, okay, I'm looking at a circle. You could even see it in this form. X minus k squared over r squared plus y minus h squared over r squared equals 1. And I'd want you to know you were looking at a circle centered at k comma h. You'd switch the signs to find the center. And you'd have the radius squared down here. This seems like a bit of extra work, but there's an interesting way to think of an ellipse in general. Remember, a circle is just a special case when the plane slices through the cone perfectly perpendicular to the cone's central axis, the center of the cone. Put a plane going perfectly perpendicular to the direction of your right cone, your right circular cone, and you get a circle. Tilt it, and you get an ellipse. Ellipses are symmetrical. That's important to understanding them. I'm going to graph an ellipse. If an ellipse is centered at the origin, and I'm going to do an ellipse that's more wide than it is high. So I'm going to do an ellipse that goes up 5 units. Goes to the right 5 units, excuse me. And goes to the left 5 units. And goes up 3 units and down 3 units. I can't draw an ellipse that goes, well, I can draw an ellipse that goes 5 units in all directions, but then that's just a circle. And when you're graphing an ellipse, they are symmetrical. They don't really look like eggs, because eggs aren't usually symmetrical. They're usually heavier at one end. An ellipse should be perfectly symmetrical. Mine is not. A really good ellipse will look just like Stewie's head on Family Guy.
Football.
I've never
Yeah.
seen everything.
What kind of teenage boy are you guys? Anyway, let's make this better.
Do you want me to go get you this kid's compass?
No, I'm just going to give up, because that's not important to the concept here. One way to think of an ellipse is to think of it as a circle where the radius keeps changing. That's not a very good definition, because the whole definition of a circle is the radius doesn't change. So it's a lousy definition, but it's an interesting idea to think of it that way. If this was like a circle with a radius of 5 and the radius shrinks to 3, when you're going perfectly horizontal, the radius is 5. When you're going perfectly vertical, the radius is 3. And it changes from 5 to 3 constantly in between. Can you guys picture that?
Yeah.
Okay. Good. Because that's where that's the whole point to writing a circle in this
It's
form.
kind of like when you go on a roller coaster, or not really roller coaster, one of the things that spin you around. I think it starts
Oh, some of those
straight
rides
out,
that-
and then it starts to turn, and you
Curve
like
in.
go up onto the wall.
In physics, we'll talk about that in
Yeah,
greater
that's what I
detail.
thought.
One reason to think of an ellipse as a circle where the radius keeps changing is because it lets us change this equation for the circle into this general equation for the ellipse, where a, the square root of this number, is going to be my horizontal semi-axis. What does horizontal semi-axis mean? Well, first, what does horizontal mean? Everyone's doing the right gesture? Yeah, it's
Perpendicular to the y-axis.
yeah, perpendicular to the y-axis. That's perfectly said. What do you think the semi part means?
It's not entirely.
It's actually more than not entirely. It's perfectly cut in half. So whatever this number is, this ellipse goes from its center out to 5. It's exactly half the total distance across the ellipse, the long way in this case, the horizontal way in general. We're going to use A for the horizontal part. This will be a little different from your book. I'm going to use A as what's under the X all the time. Okay? This one is B, the square root of this number, is your vertical semi-axis. It's exactly half the total height of your ellipse. Now, your book will use A for whichever one's larger and B for whichever one's smaller. I don't do that. I stay consistent. I keep A with X and B with Y the whole time. So my notation is slightly different from the book's notation. You got that, Tim? Because I love that you double check the book, but I'm trying to remember to tell you when it's different from the book. So I'm going to express the next couple ideas a little bit differently. If you like the way the book does it better, that's fine. Let me know. I'll tell you how to remember how they do it. I just find it easy to remember. Keep it alphabetical. X, Y, A, B. X is horizontal, A is horizontal, Y is vertical, B is vertical. That makes this next equation I'm going to give you a little bit more complicated. Because yesterday I told you that ellipses had foci. And I showed you, before we started recording, a little diagram on the computer that showed the two foci of an ellipse with those spheres. What's really important about ellipse is often where the foci are. If you want to build one of those pool tables I talked about yesterday, that can be, if you want to design one of those rooms where everything's set at one foci can be heard at the other, you need to know where to put the foci. First off, they're going to be inside your ellipse by definition. Okay? They're going to be inside your ellipse. And the equation for this is c squared equals the absolute value of a squared minus b squared. Different books will do this differently. A couple of things to note. One, this looks a lot like the Pythagorean theorem, but the absolute value sign and the subtraction sign are different. That can help some kids remember this, because the Pythagorean theorem has a lot to do with how Descartes came up with his equations for these conics. Don't mix this up with the Pythagorean theorem. Okay? Another thing I haven't said yet, c is your distance from the center of your ellipse. Should define this first. C is the distance from the center of the ellipse to a single focus. And you need to know that both foci are always along the larger axis. Both foci are always along the larger axis. So the foci of this ellipse, are they going to be along the vertical or the horizontal axis? Foci of this ellipse, are they going to be along the vertical or the horizontal axis? Horizontal. They're always along the longer axis. Always, always, always. How far are they? Let's find out. We'll plot this formula. Oh, this formula resembles the Pythagorean theorem. Second thing, I always remember that the ellipse has a subtraction sign in this formula. The way I always remember that, your foci have to be inside the ellipse. That means the distance from the center to the foci has to be smaller than 5 in this case. It has to be smaller than this number. If something's going to get smaller, that's going to be because of subtraction. When we get to the foci of the hyperbola, it'll look like this, but it'll have addition. You have to be careful not to mix them up. So in this particular case, c squared is the absolute value of 5 squared minus 3 squared. Anyone know a hint for knowing what number c is going to be? Nope, not yet? Okay, we'll see where this goes. What's 5 squared?
25.
3 squared?
9. 16.
So what's c?
4.
Plus or minus 4, but well done.
Because of the absolute value.
Yeah. Well, no, plus or minus 4 because of the square root.
Oh, yeah, right.
Also plus or minus 4 because there's 2 of them. There's one of them positive 4 units, 4 units to the right of the center, and there's another one 4 units to the left of the center. So that's where the foci would be on this exact ellipse. What would the equation of this ellipse be? Well, where is its center? This ellipse I've graphed. The origin, 0, 0. For space purposes, I'm just going to fill in this equation. All right? So for this one, h and k are both 0. Do I need to write x minus 0 and y minus 0 squared? Can I just write x squared and y squared in this case? Yes, I'm seeing nods. That's good. What will a squared be for this particular ellipse?
Wait,
For this ellipse I've drawn, what will the number a squared be?
25.
25. What will b squared be?
No.
9. So you need to know this forwards and backwards. You need to look at a picture and fill in what this equation will look like. You also need to be given this, you'd be able to be given this equation and go back and graph it. I don't know how much more time I have to do an example of that, so I may just have to take some extra questions, maybe some time tomorrow to take questions on the homework. Notice there's nothing in here that directly tells you where the foci are. You have to subtract these two numbers, take that absolute value, and take the square root to find the foci. Okay, we'll probably go over more examples of that tomorrow. I'm going to save eccentricity for tomorrow. I don't think you need that for the homework, but we're going to talk about eccentricity tomorrow. That's important. And there was something else I wanted to say about ellipses that I want to make sure to move forward. Just, pardon?
Did you say Robbie or Brody?
I'm not sure I said either.
He didn't say, well, it's
No,
our
you
day.
said Robbie.
Okay. Any questions on using this to find the foci? Okay. I don't think you need to know the eccentricity for what I assigned for tonight. Let me. Oh, I know what you might need. Just enough time to do it. Let's say for this particular ellipse, you don't like writing it this way. How could you get rid of both those fractions? What would you have to multiply every term by to get rid of both those fractions? 25 and 9, right? Remy? Yeah, you don't even need to know that answer. You need to multiply both of them by 25 times 9. Well, what is 25 times 9? Oh, please, gentlemen.
Yeah.
Very good. How'd you do that?
It's a-
Or 25 times 8 is 200, so plus 1 is plus 25.
Awesome. So you did
Or
25
times 10.
times 8 plus 1 is 200 plus 25. What did you do?
25 times 10 minus.
25
I
times
just
10
did-
minus 1 is what I did, is 250 minus 25.
I just did 5 times 9 and then 20 times 9 put them together, but that took longer.
I actually have trouble with that in my head.
Oh, I can do that easier than
You're going to want to start thinking about some tricks like this, because you're going to have some problems like this without, we're going to do a lot of this without calculators. Either way you look at it, you're going to multiply everything by 225. When you do that, when you multiply 9 times 25 times x squared over 25, I'm going to leave 225 as 9 times 25. The 25s will cancel.
Oh, no, the other side is the 9 will cancel.
Very good, Danny. And the 9 times 25 y squared over 9, the 9s will cancel, and 1 times 9 times 25 is 225. So what you get is 9x squared plus 25y squared equals 225.
A good example of, for example.
But don't erase.
Thank you.
Or,
It's actually the same extended example. Going from this form to here isn't that hard. Going from here back to there when it's not centered at the origin is a little bit more difficult and requires completing the square. And you may have one of those in your homework tonight, so let me see if I can find a quick example. I hope you remember completing the square. I apologize to get this done in time. I'm going to have to rush it a bit. I should have had this one a little bit more ready,
you spend
but
too much time looking at that thing on your computer.
I thought that was a useful setup for the lesson. But yeah, we did spend a little too long looking at it. Okay. Give me 1 second. These I don't make up off the top of my head. So on a good day I can, but I don't want to come up with a bad one.
Is this another example?
Yes, I'm going to do a new example in a moment. I'm going to erase all of that in 1 second, so please be ready. And let's see. Okay, that's not a good one. That's not a great one. Okay, that'll work. We'll talk more about the general form of a conic later this week, but for today, let's say you are just handed something like this. Example. I'm going to throw everything we've done into one big example. It's a big jump. So are you guys ready? Braced?
Good.
That's the enthusiasm I want to hear. That, believe it or not, is either a circle or an ellipse. And by sometime next week, you will know from just glancing at it that it's either a circle or ellipse as well.
We'll be able to decide which one it is, or we'll
You'll be able to decide which one it is before you look at it. You probably won't know much more about it until you do the steps we're about to do. Our goal is to change this into x minus k squared over a squared plus y minus h squared over b squared equals 1.
so we can graph it.
Yep. You don't want to try and graph it from here. Not by hand. First thing, step 1. Gather like terms. So I'm going to make 16x squared minus 8x plus 16y squared minus 32y equals 127. That's your step 1. Step 2, factor. What we're about to do only works if x squared is by itself and y squared is by itself. Oh, this one's going to be ugly. So this needs to become 16 times x squared minus 1/2 x plus 16 times y squared minus 2y equals 127. Any questions on that in the 3 minutes I have? Step 3, complete the square. Hopefully you remember this, but completing the square is the idea that we'd like to have what's called a perfect square trinomial. Something that we can change from a trinomial to a binomial as a perfect square root. And the way you always get that is you cut this number in half and then square it. What is half of 1/2?
4.
And what is 1/4 squared?
1/16.
1/16. Very good. What is half of 2? Of negative 2? That one should be a stumper. I know you guys are writing fast. I apologize.
1.
But half of negative 2 is negative 1.
Yeah.
What's negative 1 squared?
1.
1. So I really want there to be a plus 1 there. Now, am I allowed to just add a 1/16 and a 1 wherever I feel like?
No.
Well, this is America. I'm free to do that. But we're a free country, but we're also a capitalist country. If I do that, I have to pay for it somewhere else. Where am I going to pay for that? Where am I going to
Out
pay
of
the
your
cost between a
wallet?
1/16 and a 1? Pardon?
Out of your wallet?
No, I'm just going to pay for it on the other side of the equation.
Okay.
Now, here's a bit of a trick question. Did I really add 1/16 here?
No.
No, to this side of the equation, I did 1/16 in the parentheses, but that was being multiplied by 16. So 16 times 1/16, that's just 1. I actually added a 1 to this side. I added a 1/16 in the parentheses, but the entire parentheses was being
Oh,
multiplied
right.
by 16.
That makes sense.
So to pay for this 1/16 in here, why
Wait a
did I put
minute.
a plus 1
But
over
then
here?
you have a 1
In here, so what did I really add to this side, Dan?
16.
Yep. Now, once you have your 1/16 here, here's what we can do. This will always break down to x minus, in this case, minus 1/4 squared. Remember we started by cutting this middle term in half? That will always be the second term of your binomial after you're done completing the square. This one will now break down to y minus 1 squared, and the other side now equals 144. I apologize for the speed, but are there any questions on the step? Anyone watching at home, this should be high enough quality that you can freeze this frame and look at the steps. You have to remember, though, if you add inside the parentheses for the completing the square part, to multiply by that coefficient. I am now going to divide everything by 16, which gives me x minus 1/4 squared plus y minus 1 squared, and I happen to know equals 9. 144 divided by 16 is 9. You'll get good, some of these numbers will recur. So I now know that this was a circle. Write the answer in red. I now know that this was a circle. Don't move yet. I know its center is at positive 1/4, positive 1, and I know its radius is 3. And I could graph that circle from there. Any quick questions on that? Again, I apologize for the rush on it. Homework is online, and I don't have it printed, and I'll tell you right after. I have it on my iPad. I can tell you right after we're done recording.
It's not on the wall.
No, I haven't printed it yet. I've done everything else. Okay. That's the most fun this unit gets.
That's pretty impressive.